All right, a lot of information on this slide. Let me break it down. Over here is the titration curve of our analyte acid, what we call HA in this example. Now imagine that we have two beakers of this HA acid. But in one beaker, we've added 3 drops of this methyl red indicator, and in the other beaker, we've added 3 drops of thymol blue indicator. And so these indicators are along for the ride as the main acid is being titrated. Now let's focus on methyl red. Its acidic form is red, its basic form is yellow, and its pKa is 5.0. So based on the notes that we wrote earlier, if the pH is lower than 5.0, then we will have more of this red acidic form than the yellow basic form, and vice versa. If pH is greater than 5, we'll have more yellow than red. That being said, if the pH is close to 5, let's say 5.1, while we would have more of the yellow basic form than the red acidic form, we'd still have enough of this red species in the mix that we could see that red and it would blend with the yellow species that's also there, and we would just get some shade of orange. And so in order to have one of these species so much more dominant over the other that we only effectively see their color, we need to get away from that pKa value. And that's why we have transition ranges for these indicators. If we are at 4.4 or lower, the red acidic form will be so dominant over the yellow basic form that we effectively will not see this. The solution will look red. But once we get beyond 4.4, we'll start seeing different shades of orange until we get so far above that 5.0, in this case 6.2, that this yellow form just completely dominates. There's almost no red acidic form left in solution, and we would see yellow. But between 4.4 to 6.2, we would see lighter and lighter oranges as the pH was getting higher. Similarly, with thymol blue, its pKa is at 8.9, so its transition range is around that pKa value. Between 8.0 to 9.6, we will see a mix of yellow and blue species. But if our pH is below 8.0, we'll have this yellow acidic form, and if we get above 9.6, we'll be in this fully blue basic form. But in between, we'll just get darker and darker shades of green as we transition from yellow to blue. And so now let's watch this in action. So I'll direct your attention back over to the curve. Let's imagine we're at the very beginning, signified by this purple ball. So our pH is 4. That's below both of these transition ranges, and so in each beaker we primarily have the acidic form, and so red and yellow. Now I'm going to start this animation, and this purple ball will move to indicate where on this titration curve we are, and we'll just watch what happens in each flask. Here we go. 3, 2, 1, start. So the pH is now above 4.4, and if we look over here, it's starting to change color. It's getting orange. It's transitioning to yellow. pH is still not out of the transition range, but now it just reached 6.2, and we are yellow. Nothing's happened here yet because we haven't reached this transition range. We're still below 8. But wait for it. We're about to reach it. And then we are now in the range, and as pH rises, this becomes more and more blue. We're having green shades, and now we're at blue because our pH is above 9.6. And from here on out, this solution will continue to be blue. Notice this one is still yellow because we've only gotten higher and higher than that upper range. Now, you may have noticed these notes popped up during that animation, and these represent the volumes of the endpoints. Let's remember what endpoint is defined as. It is not the equivalence point, it is just the point where the color changes. That's what you wrote down before. And so for this indicator, in this particular titration, there is no specific volume that caused the color to change straight from red to yellow. It happened over a range of volumes where we had orange in between, because if we look at this curve, we don't enter that transition range until about 1 milliliter in, maybe a little less, But we don't exit that transition range until we get to 6.2 as the pH, which is over here. And so it takes quite a bit of base to cause that color to change. And notice the volume where the color change occurs does not overlap with the equivalence point itself at all. And that is why I stressed the endpoint should happen at the equivalence point for it to be meaningful. But it's not a guarantee. It depends on the indicator. Methyl red is not a good indicator for this titration. On the other hand, thymol blue works great because we imagine we're titrating, we get right up to that equivalence point, our pH is at 8, we're still pretty much all yellow, and then we add like a drop or two, and then bam, we hit the equivalence point, pH skyrockets, and we are well out of that transition range. We never see the green. One moment, we're at pH 8, everything's yellow. One drop later, pH is skyrocketed, we are blue. And so we have a legitimate endpoint volume where just a very specific volume of base, somewhere in between 9.9 to 10 milliliters, causes that color change to occur. And that endpoint overlaps with the equivalence point. So that's why I said they should happen at the same time, but they're not guaranteed to happen at the same time. And I want to stress that if you have an appropriate indicator, it only takes 1 or 2 drops of titrant to cause the color change to happen, just like what we saw in that titration video I showed before. We can see that the solution has actually turned color. It is hard to see with the camera, but hopefully you can tell that that is no longer clear. It is a faint pink, right? So what I'm trying to really get at is that the only way that a color change could occur from a small addition of base, like a drop or two, is if we were at the equivalence point, because that's the only time in the titration curve where we can see a little volume goes a long way as far as changing the pH. Anywhere before, anywhere after that sharp region, it's going to take a lot more than a drop or two to cause the color to fully change. So that's why an indicator is not guaranteed to work. It must be chosen appropriately. Now, I really want you to understand this concept, the difference between an endpoint and equivalence point, because it's just such a giant misconception for most students, particularly when they learn about it in Gen Chem, and it's all new to them. So let's make sure we get it with one more slide and visual. So imagine we have some acid that in theory would give this curve upon being titrated with some strong base. And let's say that we add an indicator that changes color from pH 9 to 11, from, in this case, yellow to purple. Well, we can see from the titration curve that the equivalence point happens at 25 milliliters. That's our sharp region. And the pH at the equivalence point is right around pH equals 10 because that's the middle of the sharp region, which is the estimate we're going to use in this class. As far as the indicator is concerned, well, that endpoint matches the equivalence point because we would be yellow right up till we got there, then we'd add that drop and we would shoot past the range and be purple. So this is a very suitable indicator for this titration because both the equivalence point and the endpoint will overlap very nicely. But what about this acid? This acid has its sharp region occur still at 25 milliliters, but then it takes a little while to come out of it. So let's estimate that the equivalence point is still 25, that's the sharpest part. Let's say the pH is around 8 at that sharp point, it's probably less. But the indicator is not going to change color until we reach a pH of 9. And it won't complete its color change until we reach a pH of 11, which we can see takes some volume past 25. So the color would not change from just a drop or two. It would actually take like 1.5 milliliters according to this titration curve. So it's not a great overlap with the equivalence point, and it's not the best indicator. Now let me show you a really bad example. Here's an acid who upon titration still has its equivalence point at 25 milliliters. Its pH is at about 8. However, if we think about what would happen during the titration, We would reach the equivalence point, we would add the drop, skyrocket the pH, but our indicator would still be yellow because we have barely started to enter its transition range. Then we would add base and we would gradually get more and more purple, but we'd still have that yellow in there, and it looks like it might never actually fully rise out of that range. And so we would see, starting at 25 mils, the color might change, and then over 50 milliliters later, color is still changing. It's a terrible overlap. We're not going to have that immediate color change from a drop because the transition range of the indicator does not overlap well with the equivalence range of the analyte that we're studying. And so this would be a very bad indicator for this particular titration here, even though it works so well for this titration. And so final points, which you might want to write down: the indicator will always change color over its given pH range, regardless of whether it matches the sharp curve, i.e. the equivalence region of the titration. And the titration's equivalence point will happen at the sharp region of the curve, regardless of if that's in the color change region or not. And so I want to finish this video with a final thought. In these earlier titration labs that you've probably done before, you kind of take it for granted when the teacher or the manual says, use this indicator, typically phenolphthalein. But usually there's some trial and error that goes into figuring out what indicator is best. We've just already done it for you. So let's finish the video with a clicker, which of course we'll do in Zoom, but you can at least see it now.